So let's start with a merry-go-round. And this is going to be an angular momentum example. So we're talking merry-go-round like at a park. So let's give it a diameter of 3 meters. It's about the size of what I would normally see at a park. Let's say it has a mass of 150 kilograms. And let's say that the merry-go-round is just a simple disc. They have handles and stuff, but let's just treat it like a simple disc, okay? Now let's say that 4 friends show up to play on the merry-go-round. And let's say that they are of generous proportions, and each friend is 60 kilograms. And they are standing on the edge of the merry-go-round. Why don't you take a moment and figure out the moment of inertia of this system? Got 5 objects. Each has a moment of inertia. We'll assume that the system is going to spin about the center of the merry-go-round. So you will have to make an assumption, and you'll have to do some calculation. I'll give you about 2 minutes before I call out on somebody. So talk it up at your tables. That's about as much time as I want to give for this. You guys should be about done. Caitlin, what do you got here for the moment of inertia of this system? Around 708. Are you saying that because it's round?
No.
Can you tell me what you did to get there? Because I think that would be helpful for some frustrated folks.
Okay. Well, first I found the moment of inertia of the merry-go-round, which is the disc.
Okay.
So 1/2 r squared. And then the mass is the 150, and the radius is the 1.5.
So you got
168.75.
You know the units? That one, kilogram meter squared.
Okay.
Excellent. That gives us just the disk. And is that it? Is that the only moment of inertia there is? What else do we have?
We also have the 4-point masses.
4-point masses. Here's where you had to make an assumption. You treated them like point masses. Can you give me a good reason why to treat them as point masses?
They're added on the ends.
I'd say there's 2 reasons why it's probably good that you could treat them as point masses. And I've talked about them in class. What are the 2 reasons you think? Yes, sir?
Well, they're not like directly, there's nothing in between connecting, there's nothing other than the disc, which we've already accounted for.
Yeah, but I wouldn't have said that in class. Yes, sir?
The radius that they are from the axis of rotation is larger than their internal radius.
Yeah, the axis of rotation is outside their body. That's almost always a dead giveaway. Also, did I give the size of their bodies? No. Those are 2 giveaways. That's why you're going to use them as point masses. So you're right. There are 4 of them. They're each 60 kilograms, and they're each 1.5 meters away from the center. So you run that, and you get, what, 540? You add all that together, and the 540 plus the 168 is where you get the 708.75 kilogram meter squared. That is the moment of inertia of our system. Excellent. Excellent. Any questions about that? Relatively straightforward. Let's say a friend of theirs comes out to spin the merry-go-round. Okay? Now, I try to use as realistic a number as possible for stuff like this. So I'm thinking if I spun kids on a merry-go-round, 1,000, 2, 1,000, it seems like 1 revolution in 2 seconds seems like a reasonable speed for a merry-go-round. Would you guys agree? I mean, from that count, it seems all right. So I'm going to say it makes one rotation every 2 seconds. Can you turn that into an angular speed? I would hope so, but all day today I've been disappointed. So it seems like my initial speed is one rotation every 2 seconds, or half a rotation per second. 0.5 RPS, rotations per second. Questions? One rotation every 2 seconds. Although, for what we're about to do next, radians per second would probably be best. I would like you guys to calculate the angular momentum of the system and the kinetic energy of the system. The angular momentum and kinetic energy. You will need to have our angular speed in radians per second to do so. Remember, angular momentum, I times omega, and kinetic energy we've done dozens of times already, so I don't feel like I have to tell you too much, but I'm putting the I in there for initial. Let's see what we got. Start with angular momentum first. Oh, I don't know. Let's see. Adam? I know I have two, so why don't one of you guys flip for it and tell me what the answer here.
For energy? Or no,
No, I want the angular momentum.
angular momentum, I got, 2,200, or, yeah, 2,226.
I think you're right, 2,227. And the units here are funny, kilograms, meters squared per second. So we just took the total here, moment of inertia, and multiplied by 0.5 rotations per second, but converted to radians per second, which is 3.14 radians per second. There's multiplied by 2 pi. All right, so the other atom, what do you got for energy here? 3,493 joules. That's it. 1/2 I omega squared. All right, so that's doesn't tell us very much. These are just numbers. And by numbers, what I mean is they don't have any meaning to you. You don't know if these are big numbers or small numbers. You don't really fully appreciate the size of the numbers. That's not what this is about. You want to see what happens when something changes. That's what's going to be important. So here's what's going to happen. And you guys need notes that help you. So I'm going to give you some things to think about. All of these people walk towards the center. This is going to change the moment of inertia. But the kid on the outside doesn't touch the merry-go-round. So the kid on the outside doesn't apply a torque. This is a closed system. How fast is it spinning after they walk to the center? Now, no, I'm going to give you a distance in just a minute, but I just want to make sure we understand something. One of these two numbers doesn't change. And if you're paying attention, you probably know, but let me just be clear. This is a conservation of momentum problem. So the angular momentum stays the same. I'd like to know how fast this is spinning after they walk to the center. Now, they can't walk all the way to the center or they'll overlap each other. So when they get to the center, let's say that they are 20 centimeters from the center. So they all form a little kumbaya circle in the middle where they're all touching and hugging each other. They're friends. Don't make it weird. So they are 20 centimeters away from the center. I'd like to know the new angular speed. But while you're doing that, no reason why you couldn't find for me the new kinetic energy too. Because that's what I really want to know. And you got to hustle. There's 2 minutes. Now you got to go fast. So I put the moment of inertia up there for what you have to do. The disk doesn't change. It's still 168.75. But suddenly the people are now only 0.2 meters from the middle. This does dramatically change the moment of inertia. This is why pulling the books in makes such a big difference. Remember, the angular momentum is still the same. This number is still the same. So this has to equal I final times omega final. You're finding I final right here. Got to move. That bell's going to ring. All right, should be about done, at least for the angular speed. 12.5 radians per second. So it's about 4 times faster when those kids walk through the center. Now we need the energy. That's the crux of this. That's what I need you to see. So now that we have the new speed, bring on the energy. 1/2 times I times omega. Make sure you use the new I here. Come on, I need it. Who's got it?
13,900.
13,900 and what?
5.
I want this so that people who are still a little lagging behind have a number. Now, before you guys pack up, look, I understand, long day. This was the original energy. The momentum didn't change, but we've got a lot more energy here. Almost 4 times the amount of energy. Where'd it come from? There's no torque. The kids didn't have an external torque applied to them. So where's this energy come from? I mean, every other collision we did, we saw energy left the system in conservation of momentum problems. Here, energy comes out of thin air. This is why you need to sit on a stool. This is why you need to try this. The kids did this. The kids pushed against the merry-go-round to get themselves towards the center, right? They're feeling like they're being flung off the merry-go-round, being flung to the outside. They had to work against that to get themselves to the center. That added energy to the system. When you pull your arms in, you'll feel it as you try to pull those books in.